Hello, and welcome to our presentation on 3D science learning in agriculture through sustainability. My name is Craig Cohn, and I'm a doctoral candidate at Michigan State University in curriculum instruction and teacher education. So much of our presentation will emphasize preparing students for the future of agriculture. And from the surface, that future looks pretty productive and successful. For example, since the 1940s, agricultural output has more than doubled, while inputs have remained relatively constant. However, if we look below the surface, we can see some clear concerns. We'll need to produce a lot more food using a lot less farmland in the next 30 years. And we know that conventional egg production in the United States is not well prepared for changes to precipitation that are coming. We also know that American agriculture is a leading cause of water contamination, and that most farmland is not cultivated using sustainable soil management practices, leading to a very high rate of soil erosion. We also know there are other concerns. For example, there are large wealth and income disparities between U.S. farms and a rising rate of farm bankruptcy, especially in recent years. So we have to ask ourselves, what is the purpose of agricultural education? Are we merely trying to recreate the status quo of agriculture, problems and all? Or are we trying to prepare our students to be change agents in order to make a more sustainable, viable, and efficient agriculture industry? And so the overall objective of this presentation is to ask ourselves, how can we design agricultural education to enable more informed and more sustainable decision making? This presentation will have three parts. First, we'll summarize the research in science education that tells us how we can accomplish this goal. We'll then discuss our own research-based efforts in trying to create this for agricultural classrooms. And we'll conclude with how you can apply this in your own classrooms in order to enable more informed decision-making among your own students. To begin, we'll summarize the research that's contained within the framework for K-12 science education and the next generation science standards, as this is the basis for our work. In the late 2000s, there was a wide body of research that suggested that there were a lot of problems with traditional K-12 science education in the United States, mostly in that it was not sufficiently preparing students for their careers or for informed decision-making. This posed significant risks to the United States, both in terms of our economic standing and our national security. As a result, the National Research Council published the Framework for K-12 Science Education in 2012. This document is a consensus of 2 decades of rigorous scientific investigation into what constitutes effective K-12 science and engineering education, especially for the purpose of enabling more informed decision-making. To date, most states have developed new science standards based directly on the findings contained within the framework. In 2013, a group of nearly 24 states led an initiative to create internationally benchmarked science education standards based on the research contained in the framework. And these are now known as the Next Generation Science Standards, or NGSS. Both the framework and NGSS argue that in order for science education to be effective, it must be three-dimensional, or composed of 3 interconnected components known as disciplinary core ideas, science and engineering practices, and cross-cutting concepts. So what are these things? Well, we can see on the left-hand side in the orange square, we have a summary of the disciplinary core ideas contained within the Next Generation Science Standards. We're trying to get away from the mile-wide, inch-deep approach to education in which we try to teach as much content as possible, in which it's mostly just a memorization of facts. And we're trying to get students to reason more deeply about core ideas that provide broad explanatory power across all of the branches of science. In the top right, in the blue square, we see science and engineering practices. And this is what scientists do. This is how scientists find solutions, create explanations, and solve problems. And so we can see things like asking questions, carrying out investigations, and engaging in argument from evidence. And these are skills that we want to teach students in order to enable them to systematically reason about the world and develop solutions. And finally, in the bottom right, in the green square, we can see cross-cutting concepts. And these represent how scientists think. This is maybe the most elusive of these 3 components, as this is something that isn't traditionally emphasized in science education. However, this is a key way for scientists in order to determine if their solutions are valid or if their conclusions make sense. So for example, if you're going to interpret a graph, you might look for patterns in that graph. You might look at the X and Y axis to determine cause and effect. The scale and proportion of changes in that graph would also give us some idea of what that graph is trying to tell us. And so all of these things are key in order for scientists to reach a valid conclusion. And all three components are seamlessly necessary in order to train students to reason systematically and develop valid solutions and explanations. So we often say that 3D science instruction is more about figuring out than learning about. In 3D science instruction, we are emphasizing sense-making and reasoning over memorizing rote content. And we want students to be able to use both knowledge and practice in order to create explanations and develop solutions. So for example, in traditional biology, students would learn about photosynthesis. They would memorize terms, look up structures in the cell, and see how those things work in terms of a process of photosynthesis. However, in three-dimensional science, we would have students figure out how plants make their own food. We would engage students' investigation, have them collect evidence, argue about potential explanatory models, and eventually collaboratively develop explanations in order how plants make their own food through photosynthesis. So we can see a comparison between 3D science and traditional science, in that 3D science is really not about content, but about engaging students in developing questions about phenomena. Rather than emphasizing learning facts and procedures, we're maximizing our emphasis on reasoning and sense-making skills. In 3D science, science and engineering practices are not just a standalone lab or a unit on the scientific method. They're an integral part of education and occur in every step in every unit. We see that content and practices are a seamless part about reasoning about natural phenomenon in a way that's learning and relevant, in a way that's relevant to the learning of all lives of all students and incorporates their background and prior ideas. So in terms of assessing 3D assessment, we know it looks very different than our traditional multiple choice tests. Often we see three categories of assessment questions that help to guide towards students in enabling them to develop their reasoning and sense-making and express that in an assessment. So for example, we might ask students about what kind of evidence they might need in order to create an explanation or develop a solution. We might provide students with evidence and ask them to address claims using that evidence. Or we might ask students to reason about the claims of other people. So for example, we might provide them with 3 different claims and ask them to determine which of those are accurate, which are inaccurate, and why. You'll notice in all 3 of these cases, we're always asking students to explain their reasoning, because again, reasoning and sense-making are at the core of what it means to do 3D science learning. So now we'll talk briefly about how we've tried to attempt to create this kind of learning in an agricultural classroom. Agricultural education and science education are 2 different subjects, and while there's a lot of overlap, creating an NGSS-aligned agricultural education curriculum is something of a challenge. And so the reason this curriculum exists is to support students and teachers in the process of shifting and transitioning over towards more 3-dimensional agri-science instruction. So FACS, or the Future of Agriculture Curriculum for Teaching Sustainability, is a research-based 2-semester high school agri-science curriculum. This involves a natural resources and a horticulture plant systems course in the fall and spring semesters. These courses are aligned to both the NGSS and AFNR academic standards, and supervised agricultural experiences are explicitly incorporated into the curriculum. This curriculum is freely available online at facsnsf.org. This curriculum is the outcome of a 5-year NSF-funded research project at Michigan State University. And the goal of this research project is to maximize the adoption of more informed and more sustainable practices among future agriculturalists. This research contains both education and social science research components. So we're not only in classrooms, we're also working with farmers, agricultural scientists, and other professionals in the agriculture industry. This is design-based research. This means that we're working directly with practitioners in the field in both education and agriculture in order to get their feedback, test their ideas, and refine them. This work is also ongoing. And so if you go to that website, you'll see continuous changes to the curriculum that are occurring as we get feedback and ideas from the people we're working with in the field. And so the idea is that this is an iterative research project that's responsive to the needs of people in the actual industry and in classrooms. Our curriculum uses what we call a 5-day structure. Now, often this takes more than 5 days, but we try to create a consistent structure in order to support student learning outcomes. So on day one, we provide students with basic case study data and ask them to explain their ideas and develop explanatory models surrounding this data. On day two, we provide them with scaffolded core instruction so that they can refine their explanatory models and deepen their reasoning. On day three, students have an opportunity to test the validity of their explanatory models in collaborative investigations. On day four, we have review and assessment. And on day five, we have career and community connections, where we explicitly incorporate things like SAEs, college and career preparation, and community involvement into our classroom instruction. These 5-day units end in sectional assessments that occur in real-world contexts over multiple days. So as an example, we have our habitat loss unit in our natural resources course. This unit occurs after students have considered how matter and energy interact in ecosystems across the atomic to the ecosystem levels. And this occurs after an introductory unit on extinctions and how the loss of biodiversity affects human activity like agriculture. So on day one in this unit, students are provided with data from an experiment by Gonzalez and Chainton, in which they fragmented habitats for insects and measured how that affected insect biodiversity. We asked students to explain their initial ideas and collaboratively develop explanatory models that they will refine over the course of the week. On day two, we provide scaffolded instruction on the island biogeography model. This explains how habitat fragmentation and habitat loss relate to loss of biodiversity and how that affects ecosystem services. On day three, students go into a local habitat, such as a school forest, to see if they can find evidence of any of these things occurring in their local community. On day four is review and assessment, and on day five, we have career connections. Students begin by reflecting on their SAE experiences to see how this might have been occurring in their local communities. They're asked to reflect how this might affect decisions they make in their future careers, and then they engage in college and career preparation. In this case, that entails writing and developing their cover letter and resume. The FACTS curriculum really depends on models and argumentation as the core means of instruction in this class. So what this means is that we engage students in reasoning and sense-making to this extent that they actually develop explanatory models about phenomenon and defend those models using evidence. And so students are coached continuously in ways that are systematic for reasoning and sense-making and problem solving. And these are then connected to localized AFNR scenarios in their local communities. It's really important that we scaffold students' reasoning and sense-making and provide them with the opportunity to see models of how scientists actually go about making sense of the natural world. We often call this a sense-making toolkit. So we're not emphasizing vocabulary, although that's present, and we're not asking students to memorize processes, although those are described in the curriculum. What we're trying to do is provide students with deeper ways to reason about phenomenon in a stepwise fashion that's scaffolded. And you can see that in this example, in which students are provided with some terminology, but in a manner that isn't about memorizing those terms. It's about deepening their capacity to develop explanations and reason about phenomenon such as a carrying capacity. As I mentioned, supervised agricultural experiences are utilized explicitly throughout the curriculum as a graded part of instruction. And students are required to get 15 or more hours of career experience in a career area of their interest, and then complete a portfolio that documents those experiences and helps them to reflect on how those connect to the classroom experiences. We found this is absolutely vital in order to prepare students to make more informed decisions outside of the classroom. If we only focus on in-classroom experiences, students become very good at making informed decisions inside the classroom, but we don't have a lot of evidence to show that that transfers outside of the classroom environment. SAEs are a critical bridge between informed decision-making in the classroom and informed decision-making in their future careers. So to conclude, we'll talk briefly about things that you can do to incorporate these ideas in your own classroom. There are 3 things you can do right now, and the first is to assess your own teaching and your own curriculum. Is what you do more about learning about the phenomenon or figuring out unknowns? And one way to check this is through the NGSS lesson screener. You can either just Google those terms, or if you have access to this PowerPoint, you can click on that hyperlink. You can also start identifying courses that might be easiest to transition to 3-dimensional science learning. Some are easier than others, and so it makes sense to start this in a stepwise fashion. This is a difficult transition. Most of us, if not all of us, have never had this kind of instruction ourselves when we were students. And so it takes time and support to adjust to this kind of new way of teaching. Three things you can do over time include replacing traditional curriculum with NGSS aligned materials. Again, NGSS aligned materials have a wealth of research basis over decades that show that this is the most effective way to enable more informed decision making. This isn't about the latest fad. This is about preparing your students as much as possible for the changes that are coming to the agriculture industry. And so finding curriculum that is effective in this manner will be key for their career preparation. One way to support this is to form groups to share effective resources. These exist in places such as district initiatives, NAAE, and other options. Or consider partnering with your science department if they're also adopting NGSS at this time or have already done so. You can also seek out additional training. The National Science Teachers Association offers lots of opportunities in this regard and offer discounted membership to NAAE members. You can also consider partnering with university faculty, either in your own state or others, and often funds are available. And finally, you can ask yourself these questions continuously. Is your teaching about figuring out or learning about? Are you emphasizing reasoning or memorization? Are you assessing just knowledge or knowledge and practice in authentic contexts? And are you asking your students to recreate conditions as they currently exist, or to think critically so that they can change and improve the agriculture industry? Thank you again for listening to our presentation. Again, you can find more resources at our website, facsnsf.org. If you have questions or need additional resources, you're welcome to email me at that email on the screen. And we'd like to thank our sponsors for this presentation. Thank you again for your time, and I look forward to talking to you more in the future.